Welcome to AI Paperslop. We are jumping right into LANS, Unified Multimodal Modeling by Multitask Synergy from ByteDance.
Which is, frankly, one of the most interesting architectures I've seen all year.
Yeah, I completely agree. So here's the core insight for you right out of the gate. LANS is a highly efficient 3 billion parameter native unified model, and it natively handles image and video understanding, generation, and editing.
All in one model.
Right. All natively.
Yeah.
And it solves the inherent tension between autoaggressive language modeling, which we use for understanding, and flow matching, which is for generation.
And it does this by using a dual-stream mixture of experts architecture on a shared interleaved multimodal sequence.
Which is a mouthful, but we're going to break it all down. Plus, they add this novel modality-aware Rotary Positional Encoding, or MaPE.
Yeah, MaPE.
Right. And a staged multitask training recipe. So the result is this lightweight 3 billion parameter model that is just routinely beating massive 14 billion and 30 billion parameter generation-only models on standard benchmarks.
Which sets up really the core technical mystery for anyone building models today, right? How on earth do you fit an omni-capable multimodal model into just 3 billion activated parameters?
And do it on a compute budget of, 128 GPUs?
Exactly. I mean, 128 GPUs is basically a rounding error for a major AI lab these days.
Oh, for sure. It's nothing.
And beyond the compute, how do they do this without having the understanding and generation objectives just completely destroy each other's weights during training?
Yeah, because that's the classic problem, right? The representational mismatch.
Right. So to really get why LANS is special, we have to look at that roadblock. Historically, foundation models fall into one of two camps.
The understanding camp and the generation camp.
Exactly. So first, you have your understanding models. Think the Alava family or QuenVL.
Right.
These architectures are designed to extract these high-level, discrete semantic features. They align with language, and they optimize for autoregressive next token prediction using cross-entropy loss.
So they're built for abstraction. They want to reduce a complex visual scene into a clean semantic concept.
Yeah, precisely.
They want to know that a video shows a golden retriever catching a frisbee. They do not care about the exact sub-pixel geometric rendering of, the dog's fur blowing in the wind.
Right, they just need the concept. But generation models, on the other hand, they care deeply about that sub-pixel rendering.
Oh yeah, like Sora or Flux or Vwan.
Exactly. Those models require low-level continuous representations because they have to preserve textures, structural geometry, and complex temporal dynamics across video frames.
And they use totally different math to get there.
Right. They are typically optimized using diffusion or flow matching objectives, meaning they minimize mean squared error, or MSE, to predict continuous velocity vectors that map noise back to, pristine data.
So you are basically pitting two completely different mathematical goals against each other.
Completely.
You have cross-entropy trying to pick a discrete token out of a vocabulary, and MSE trying to map a continuous physical space.
It's a massive conflict.
It's like trying to use the exact same brain region to write an abstract philosophical essay, right? While simultaneously using those exact same neurons to precisely control the motor skills to paint a hyper-realistic portrait.
That is a perfect analogy, actually. You are asking the neural pathways to do two completely contradictory types of processing.
So how did previous models handle this? Because people have tried to build unified models before.
They have, but they usually hit that exact contradiction and had to make one of two brutal compromises.
Right.
Option one was forcing a single unified visual representation for everything. But the problem there is that you severely handicap the generation quality.
Because you've quantized away all the physical nuance, right?
Exactly. You lose the continuous details. Option two was just completely decoupling the representations, giving the model separate massive encoders for every single modality.
Which just leads to insane architectural bloat.
Oh, massive bloat. And an incredibly complex optimization landscape. You need ridiculous amounts of compute to untangle it.
But LANS basically says, we refuse to choose either of those bad options.
Right. ByteDance engineered an architecture that allows both processes to share a workspace while maintaining their own strictly dedicated tools.
And the structural solution here is fascinating. Let's dig into that workspace.
Yeah, so they start with the Qwen 2.5 VL backbone, but they adapt it pretty heavily into a dual-stream mixture of experts, or MoE architecture.
Right. And the shared workspace is what they call the interleaved multimodal sequence.
Yes, so they take text tokens And then VIT semantic tokens, which, by the way, are doing the heavy lifting for the understanding tasks.
Makes sense.
And then they take VAE latent tokens, which handle the generation tasks. And specifically for those latents, they are using the WAN 2.2 3D causal VAE encoder.
Okay, so they bring in both clean and noisy latent tokens for the flow matching objective?
Exactly. And then they take all of these radically different tokens, and they literally just flatten them into one massive single-dimensional sequence.
Just one giant sequence. If you check equation 1 in the paper, you can literally see the math for this. It's just text, then semantic vision tokens, clean VAE latents, noisy VAE latents, more text, all just depended together.
Right, and this shared interleaved sequence is the critical innovation for getting bottleneck-free context fusion.
Because of how it affects the attention mechanism.
Exactly. Think about it. Whether the model is like answering a reasoning question about a video or trying to actually generate the next physical frame of that video, all the context from every modality is instantly available.
In the exact same dimensional space.
Yeah.
But wait, I have to push back here. Throwing text tokens, high-level semantic concepts, and literal noisy pixel latents into the exact same sequence, that sounds like a recipe for absolute chaos.
It does sound like it should break.
Yeah.
Yeah.
I mean, how does the attention mechanism not just collapse? If a text token is attending to a noisy flow matching token, and they're both updating the same dense feed-forward network, shouldn't the gradients explode?
Because you've got cross-entropy and MSE fighting over the same parameters.
Exactly.
Well, that is where the dedicated tools part of your earlier analogy comes into play. Lance uses what they call decoupled capability pathways.
Okay, so the sequence is shared and flattened, but they don't process it all the exact same way.
Right. Instead of using a dense shared MLP backbone for everything, it uses specialized experts.
Ah, the mixture of experts router.
Yes. So when a token needs to be processed for semantic understanding, the MoE router sends it to the understanding expert. They designate that as LLMUND in the paper.
Got it.
And this expert specifically processes the text and the VT tokens to autoregressively predict the next token.
Okay, so the philosopher brain region gets to just sit there and use the cross-entropy loss in peace.
Exactly. While the painter gets its own dedicated studio, when the model processes the VAE latent tokens to predict velocity for the flow matching generation objective, those tokens are dynamically routed to the generation expert.
The LLMGEN.
Right, and that expert is optimized purely using MSE loss.
Okay, so decoupling these pathways is what solves the gradient conflict.
Yes, it allows the generalized 3D causal attention mechanism to fuse the context across the entire sequence, which means the semantic text can heavily influence the physical image generation.
But the specialized expert MLPs prevent the actual loss functions from fighting over the exact same network weights.
You nailed it. And that is exactly how you get away with only 3 billion parameters.
Because you aren't wasting, like, billions of weights trying to force a compromise between math that fundamentally disagrees.
Exactly. You're using the parameters way more efficiently.
But solving the routing problem doesn't solve the geometry problem, does it?
No, it doesn't.
Because even if the MoE pathways are routing the tokens efficiently to the right experts, the attention mechanism itself still needs to know where these tokens actually are in time and space.
Right, the spatial traffic jam. This is a massive hurdle in unified multitask training.
Because if a semantic token and a noisy pixel token share the exact same timestamp and spatial coordinate, the attention mechanism is just going to see double, right?
Yeah. If you have a video, you extract the VIT semantic tokens to understand the frame, and you also extract VAE latent tokens to learn how to generate it.
And if you apply standard 3D rotary positional, encoding the standard 3D RoP, the system assigns identical positional coordinates to both tokens.
Even though one is a VIT token and one is a VAE token representing the exact same physical patch of the video?
Right, because mathematically they're in the exact same spot.
But functionally, they are trying to do two completely different things.
It's like, okay, imagine trying to read a textbook where a glossy photograph has been printed directly over the text.
Yeah, you can't process either one properly.
The attention mechanism sees both at the exact same coordinate, and the softmax distribution just flattens out inappropriately between them. It just causes destructive interference.
Exactly. The model gets completely confused about functional boundaries because the abstract concept and the physical rendering are mathematically occupying the exact same space.
So how does Lance fix this? Because they can't just leave them overlapping.
Right, they fix it with MaPE, Modality-aware Rotary Positional Encoding.
Modality-aware, okay.
Essentially, MaPE mathematically slides that glossy photograph like 1,000 pages into the future.
Oh, well, okay.
So the model can process both the text and the image clearly without them overlapping at all.
So it assigns a distinct, parallel universe tag to the raw pixels versus the semantic concepts.
Yes.
How does it actually enforce that separation in the math, though?
It's actually pretty elegant. It applies a fixed offset step along the temporal dimension based purely on the index of the modality group.
Okay, so a temporal shift.
Right. MaPE takes the base 3D coordinates and it just adds a delta t of Alanson for specific tokens.
So where do the VAT tokens sit?
The VIT tokens sit at their normal absolute temporal index, no shift.
Okay, and the VAE tokens?
The clean VAE tokens get shifted forward by 1,000. And the noisy VAE tokens are shifted forward by 2,000.
Ah, I see. So they maintain their relative spatial and temporal relationships to each other within their own modality?
Exactly. Frame 1 and frame 2 of the VAE tokens are still sequential to each other.
But they are safely isolated from the VAE tokens in the overall absolute coordinate space of the sequence.
Yeah. And the empirical impact of untangling this traffic jam is actually huge. It's laid out super clearly in the ablation study. I think it's table 10 in the paper.
Right, and it doesn't just help one side.
No. Turning on MaPE simultaneously increases the image generation score on Geneval, and it bumps up the video understanding score on MVBench.
Because you've given the attention mechanism clear functional boundaries. So both the semantic reasoning and the physical generation just become more accurate.
Exactly. It clears the static.
So, okay. You have built this really elegant, traffic-free architecture, a shared sequence routed through decoupled MoE experts, organized cleanly by MaPE.
The plumbing is flawless.
Right, but an architecture is just empty plumbing until you pump data through it.
And how you pump that data matters a lot.
Yeah, how do you train a unified model to actually use this plumbing without the tasks overriding each other? Because the multitask training recipe here is, I think it reveals what is arguably the most surprising finding in the entire paper.
Oh, absolutely. The training curriculum is where the term synergy from the paper's title becomes very concrete.
So they use a 4-stage pipeline, right?
Right. A deliberate 4-stage multitask training pipeline. Stage 1 is pre-training, or PT.
Where they push, 1.5 trillion tokens through the model?
Okay, 1.5 trillion. The goal there is just establishing a massive baseline of world knowledge and basic visual fidelity. This is before they introduce any complex interleaving.
And then stage 2.
Stage 2 is continual training, or CT. This is a 300 billion token phase where they progressively introduce the complex multitask data.
Including interleaved sequences.
Yes, and it heavily focuses on image and video editing tasks.
Right, and then stage 3 is supervised fine-tuning. That's where they pull in the highly curated data, right?
Yeah, 190,000 image generation samples and 84,000 editing samples, just to enforce strict alignment and instruction following.
Got it. And stage 4 is reinforcement learning, mostly for optimizing generation rewards, like human aesthetic preference and prompt adherence.
Exactly. But the really counterintuitive finding, the thing you mentioned earlier, that happens back in stage 2, the continual training stage.
Yes, the cross-task data synergy ablation studies. This part blew my mind.
It's so interesting.
The paper explicitly shows that mixing multitask generation data, like teaching the model to edit a video, actually caused the model to score significantly higher on understanding standard videos.
Right.
Like teaching a model to swap a blue shirt for a red shirt in a generated video makes it better at answering a multiple choice question about what is happening in a totally different video.
Which on the surface makes absolutely no sense.
No sense at all. It defies the traditional logic of siloed machine learning.
But if you step back and look at how neural networks build internal world models, it is incredibly profound. This is like the very essence of multitask synergy.
Unpack that a bit. How does editing create synergy?
Well, think about when you train a model strictly on understanding tasks. It essentially learns to map a 2-dimensional grid of pixels to a text label.
Right. It learns superficial texture correlation.
Exactly. But when you force a model to perform an editing task, say, changing a car's color as it drives behind a tree without altering the tree itself.
Oh, wow. You are forcing the neural network to calculate depth.
Yes. Depth, occlusion, object permanence, lighting.
Because you cannot fake editing a car driving behind a tree.
Right.
If you don't mathematically understand that the tree is physically in front of the car, your generation objective will fail.
Your MSE loss will just spike.
Right. So learning to physically manipulate the visual elements forces the model to build a much deeper, more robust internal representation of the physical world.
Exactly. And because Lance utilizes that shared interleaved multimodal sequence we talked about, the deep physical intuition learned by the generation expert
Is fused directly into the shared context that the understanding expert uses.
Yes. The model can no longer just rely on superficial correlations. It understands the actual physics of the scene. Better physical editing translates directly into more accurate semantic reasoning.
And the reverse is true, too.
Totally. Grounding the model with complex understanding tasks improves the physical fidelity and prompt adherence of its generation.
So the philosopher and the painter are actively teaching each other.
All day long.
The capability isn't sitting in an isolated silo. It bleeds over and elevates the whole system. That is so cool.
It really is.
Okay, so we've seen the theory, the MoE architecture, the MaPE routing, the synergistic training recipe. Now, the real question for you listening, does this highly efficient model actually deliver the goods when measured against the massive foundation models dominating the space?
The benchmarks are wild.
Let's look at them. And again, keep the constraint in mind. This is a 3 billion activated parameter model trained on 128 GPUs.
Right. So these benchmark results represent a genuine disruption to the scaling laws we usually see.
How so?
Well, look at video generation. On the VBench evaluation, Lance achieves a score of 85.11.
And how does that compare?
That score explicitly outperforms massive, dedicated, generation-only models. It beats the 14 billion parameter 2.1 T2V model.
Wow.
And it beats the 30 billion parameter step video model.
So it's beating models 5 to 10 times its size that only have to focus on generation. That is insane.
And it accomplishes that without sacrificing its understanding capabilities.
Right, because on MVBench, which tests video understanding, Lance scores 62.0.
Yep. Which is the highest score among all unified multimodal models evaluated. It beats out heavily resourced models like Showa 2.
And it achieves top-tier results on JetBench for image editing too, right?
It does, but the raw numbers only tell half the story here.
Yeah, the qualitative results, what the authors refer to as emergent generalization, that is where you really see the architecture fully flexing.
Definitely. Because the model natively covers the full spectrum of image and video tasks within that shared sequence, it can perform complex edits that require intense logical reasoning and physical consistency simultaneously.
Give an example of that, because there's some great ones in the paper.
Yeah, there's a brilliant example where the prompt asks the model to replace a man's pink shirt with a Hawaiian shirt.
Okay, straightforward edit.
But then it also asks to make the man hold a coffee mug in his hand.
Oh, man. So you are altering clothing and hallucinating a new physical object into an existing grasp.
Exactly. And it executes the edit seamlessly across a continuous video sequence. It maintains the absolute identity of the man in the background while introducing these entirely new elements.
There's another demonstration I remember where the model edits a cat into a field of lavender, right?
Yeah, and it adds floating balloons behind the subject.
Right. And the temporal coherence is just flawless. Like the way the lavender moves in the wind, the way the balloons float and occlude behind the cat.
This is multitask synergy actively running.
It is understanding the semantic instruction of a Hawaiian shirt, calculating the physical occlusion required for holding a mug, and generating the continuous pixels to make it happen smoothly over time.
It really is a giant slayer.
You just have to marvel at the compute efficiency.
Oh, 100%.
Like in an era where massive AI labs are burning tens of thousands of H100s to train isolated siloed models, Lance is achieving state-of-the-art multimodal synergy on a compute budget that a mid-sized tech startup could actually afford.
It fundamentally challenges the narrative that you need astronomical compute clusters to push the frontier of video generation and understanding.
It proves that the future of multimodal AI cannot just be about scaling up parameters blindly.
Right, because brute force scaling will always yield incremental results. But Lance demonstrates that architectural elegance, using tools like dual-stream MoE to prevent gradient conflict, and MaPE to solve spatial traffic jams combined with synergistic multitask training, can create highly capable, lightweight models.
Hey, we are really looking at a paradigm shift toward efficiency and deeper integration.
Absolutely.
Which brings us to what this means for the immediate future. I want to leave you with a forward-looking question to mull over.
Okay, let's hear it.
We've established that mixing editing tasks improves semantic understanding, and mixing understanding tasks improves generation fidelity. all mediated through this shared flattened MoE sequence.
Right.
What happens when we introduce entirely new modalities to this exact architecture?
That is a great question, because the architecture of Lance is theoretically modality agnostic.
Exactly. The interleaved sequence doesn't inherently care if the tokens represent vision or something else, as long as they have dedicated routing. So if you throw audio tokens, or like literal robotic motor control tokens, into this exact same interleaved sequence and give them their own MoE experts, would we see similar synergistic leaps?
Like, would teaching a model to generate the physical sound of a glass shattering make it visually better at predicting the physics of the glass falling off a table?
Yes. Or would teaching a robotic arm to physically pick up an apple make its semantic understanding of concepts like weight and friction skyrocket?
Well, based on the findings of cross-task synergy mapped out in this research, the answer is very likely yes.
It is wild to think about.
This specific multitask synergy paradigm might fundamentally alter not just video generation, but the entire trajectory of embodied AI, robotics, and complex physics simulations.
So definitely keep a close eye on how this architecture bleeds into robotics research over the next year. Because as Lance proves, you don't necessarily need the biggest brain to understand the world. You just need to make sure the philosopher and the painter are sharing the same workspace and, learning from each other's tools without getting in each other's way.
Well said.
Thanks for joining us for this deep dive on AI paper slop. We'll see you next time.